Okay, so let's look at this next problem. A differentiable function y equals g of x is defined with the following properties. 1, g is increasing for all x. 2, g is concave down for all x. 3, g of 6 is equal to 4. And 4, the derivative of g at 6 is equal to 2, right? G prime of 6 is equal to 2. Okay, so let's look at the 4 basic shapes that all functions kind of follow, right? So I'm going to write f double prime right here and f prime. And I'm going to see what happens when f prime is positive and when f prime is negative. So we're looking at f prime. So if f double prime is positive, we know we're looking at a concave up function. And if it's negative, it's concave down. And when f prime is positive, here's f prime, then my function is increasing. And when f prime is negative, my function is decreasing. Okay, so let's draw the four basic shapes that I can have. So if it's concave up and it's increasing, I know I'm going to have something that looks like this. If it's concave down and increasing, then I'm going to have a function that looks like this. If it's decreasing and concave up, I'm going to have a function that looks like this. And if it's concave down and decreasing, I'm going to have a function that looks like this. Cool, so now let's draw a picture of what our function is going to look like. And I'm going to start off by using these two bullet points and bullet point number 3 kind of separately. So for example, here's my y, here's my x-axis, and I know that if I plug in 6, I get an output of 4. Perfect, and I know that it's increasing and concave down, so I'm going to have something that looks like in my little chart, concave down and increasing. So I'm going to have something that looks like this. Okay, and then I know that the derivative right here, using that last bullet point, that g prime of 6 is equal to 2. Okay, so since g is increasing and concave down, and g of 6 is equal to 4, then our function will never cross the x-axis to the right of x equals 6, right? That's our first justification. So here to the right of 6, it's increasing and concave down, and our point is in quadrant 1, so it's never going to hit the x-axis. But to the left of 6, we kind of have a different story, right? Because technically, if I'm traveling to the left, that means it's going to look like it's going downwards, right? And it's concave down, then it's going to have to cross the x-axis because we're in quadrant 1. And it's never going to cross it more than once, because if it were to go back up, and maybe do like a swing around, then I would have something that's concave up and increasing, right? And it can never do that, right? So I'm going to write that really quickly. To the right, I'm going to use black, to the right, or to the left, sorry, to the left of x equals 6, our values need to be going downwards. Need to be going downwards. To be going downwards. And can never go back up. Thus, G has exactly 1, 0. It must cross the x-axis once. Okay, so let's look at part B. Explain why the 0 of G must be in the interval 4, comma 6. Okay, so I'm going to really utilize this last bullet point that dg dx at x equals 6 is 2, and it is concave down. Okay, so because G is concave down for all x and G prime of 6 is equal to 2, then values to the left of x equals 6 must have slope, a tangential slope greater than 2. Greater than 2. Right? So let's look at this in terms of the picture. So here, let's say at x equals 5, the derivative must be steeper, right? Because it's concave down. The derivative must be steeper because it's concave down and increasing on this graph, right? The all values to the left must have a steeper slope, okay, than 2. Okay, so if it is 2, we see that therefore, if it is equal to 2, is equal to 2, then we can use linear approximation to see that it would have to hit the x-axis at x equals 4, right? Because I would be going down 2, right? Since the slope is 2, I would be going down 2 over 1, and then down 2, and then over 1, right? And so that would hit it at x equals 4. If it is equal to 2, then we would cross at x equals 4. Thus, our 0 must lie in the interval 4, comma 6. And maybe we can even draw a picture of what this would look like. In this instance, it's very similar to the first one, but just to be very clear for the reader, here's x equals 6, okay? And here's x equals 4, right? And it would look something like this, because g prime of 2 is equal to g prime of 6, excuse me, g prime of 6 is equal to 2. And that would cross right there. And we know values to the left at x equals 6 must have a slope greater than 2.
Okay, for part A, we're going to find the derivative of f of t, given that f of t is equal to secant of the square root of 2t. So, f prime of t equals, so we're going to have to use a chain rule here, okay? because the inner function inside of secant isn't just t. So we're going to have to use chain rule. So the derivative of secant is secant times tangent. So we're going to evaluate that at our function. Okay. And then we have to multiply that by the derivative of our function, which is going to be 1/2 times 2t to the negative 1/2. And then, since we have a function on the outside, which would be the square root of t, and we have an inner function, we're going to have to use chain rule again, which means that we'll multiply this by 2, which is the derivative of the inside of that. So to simplify this, we'd get, let's see, this 1/2 would cancel with the 2. So it'd be 1 over square root of 2t times secant of square root of 2t times tangent of the square root of 2t. Okay, that's our answer. So next, we're going to do y equals 5 to the arc sine of x. We want to find dy dx. So here, let me just write this real quick. And there we go. So when we have the derivative of this, we're just going to take the derivative of both sides with respect to x. So we get dy dx on the left side. And then if we have any number raised to a function of x, we're going to have this be our derivative. So it's the natural log of that number times the original. And since we have a function that's not just x in the exponent, we have to multiply by the derivative of that function, which from the formula sheet at the end of this practice test is just going to be 1 over the square root of 1 minus x squared. All right, for this one, we're going to find the second derivative of this function. So for the first derivative, we have to do product rule since there's two functions of x being multiplied by each other. So we're going to do derivative of the first times the second plus the first times the derivative of the second. Then we're going to combine these together. So we get natural log of x plus 1. So then we're going to do the second derivative, which is going to be 1 over x, and that's it, because 1 is just a constant. And then for number 5, we're going to find dy dx for the curve x e to the y equals tangent of y. Okay, so this one's implicit differentiation. So we're going to have the function x e to the y equals tangent y, and we're going to take the derivative of both sides of this with respect to x. Okay, so on the left here, we're going to have to use product rule again because we're assuming that y is a function of x, and we know that it is. And so we're going to do derivative of the first times the second plus the first times the derivative of the second. And when we do this, we have to bring in dy dx because we're taking the derivative of e to the y, which has a y involved. And then on the right side, this is going to be secant squared of y times dy dx. And again, that dy dx happens because we're taking the derivative of a function that has y in it. Okay, so from this point to solve for dy dx, we're going to get everything with a dy dx on one side and everything without it on the other. So I'm just going to go ahead and rewrite this, and I'm going to subtract over this x e to the y term. So I have e to the y equals secant squared y dy dx minus x e to the y times dy dx. Okay, so now since both of those terms on the right have it in common, I can factor it out. So e to the y equals dy dx times secant squared of y minus x e to the y. And then finally, I can just divide that part over. And so I'll get that dy dx equals, let's see, e to the y over secant squared y minus x e to the y. That's the final answer.